Hi everyone, welcome back. In previous videos, we learned how to run Trident and catch crashes. But crashes are the easy bugs. The dangerous bugs are the ones where the program doesn't crash, it runs perfectly, returns success, and silently does the wrong thing. Today we're learning how to catch those. We're going to learn invariant testing, how to define rules that always hold and let Trident enforce them automatically across millions of iterations as we've seen in previous videos. We'll get into it. Today we'll be using an escrow for our base testing. Most developers test this way. Before that, we go through what the escrow entails. First, we have an escrow program already built out, and we have instructions like initialize escrow, fund escrow, exchange, and all. The green arrows show like the valid flow lines, an escrow being empty at first, then an escrow initialized, funded, exchange or cancel. Then these red dashes show illegal moves, probably moving from empty to funded, double funding one escrow, then probably exchanging an escrow that has not been initialized. That also. We're going to see all of that in video today. This is the escrow program. It's already written out. We have this here. Yeah. Yeah. So most of our developers test this way. If Alice deposits 100 so her balance should be 100 so. That's the test case, but it covers only one specific scenario. An invariant is fundamentally different. It says no matter who deposits, no matter how much deposits, no matter what operations happen, even before or after, total value in the system must remain constant. It doesn't care about specific inputs. It just cares about universal variance, universal inputs. Just look at this. Universal truth rather. Yeah, we have this sequence of inputs going into an escrow program. Now, this is an invariant that says all balances must be equal to total vote, regardless of operations run on these votes, escrow, or anything at all balances at the end of all transactions must converge to get this. So that's an invariant. Unlike this here, which just says assert balance here. This is a test case, but this is an invariant. Now, most of us would write invariants, and we have three categories of invariants. I call them three categories. There might be more, but most of the invariants we write to fall under these categories. First, we have conservation. This conservation asks the question, is value preserved? Now, this is a vault. We have token A, B plus, let's say, the units of tokens a vault holds. If I add all of them, even after all the transactions, does it give me the total I started with? That's exactly what conservation says. It's value preserved. Then we have state machine invariants. State machine invariant checks if an action is legal right now. It's like checking the flow of a program. If we have an escrow program as defined here, we have empty, initialized, funded, and exchange. Is Are we moving from an initialized escrow program? Sorry, hold on. Yeah, are we moving from an initialized escrow to exchange or moving from initialized to funded? So the state machine invariant captures this kind of flows, ensuring that the program order must follow a given state. If you're exchanging first, then for any transaction given, an exchange must come first. Then we have the authorization invariant, simply asking is the caller allowed to do this? So just ensuring that person carrying out a transaction is authorized to carry out those transactions or that transaction rather. Yeah. So we'll see this invariance in code I would write in a few minutes. Then when I write invariants, I have questions I ask myself before writing them. Because writing invariants can be quite tasking and stressful or even confusing for newbies. Yeah. So the question is, how do I define or how do I determine the invariants that will fit my program or my program here? So the first question I ask myself is, what values must be conserved? Yeah. So I check my program. We have tokens, we have votes. I check maybe total token supply across all actors, across all flows. I check that and write an invariant in regards to that. Then I also check what state transitions are illegal. Yeah. So I write an invariant in that regards. Then I also check who's authorized for each action. So check what should never happen. That's a valid question when writing a program. Yeah. And then what global property must hold at the end of a sequence, yeah, of any sequence at all. These five questions like would guide you when writing invariants. You follow them through. Now, would simply go into the coding aspect, just run a few codes to actually test what these invariants do and see how our further response to them and our program. So we would move to the repo. Like I said initially, we have an escrow program already, a pre-written escrow program, and I'd already created a test harness here, like I've taught in previous videos. can simply run Trident in it to create a new test handle. But for the sake of time and this video being short and easy to watch, I've pre-created this and also written in the invariants that we need, but we just need to uncomment them, run the code to confirm functionality. Now, moving to the text first file. First, like I said, we have the conservation type of invariants here. It's value preserved. Now, check this out here. These are flows. Remember, first of all, we have the init macro where we configure accounts that we want to use throughout the entire force process. Then we have the flow macros that are model instructions in our program. Then this place, we have flow fund. That's, remember in your escrow, you initialize, you fund, then you exchange and or you cancel it, any of them. Now we have an escrow and we want to write a conservation invariant. First of all, you have to capture the states before and capture the states after. Simply that way. So you know the token value before the operation happens and after the operation happens. So here we have this line of code that does that. We'll just uncomment it. Yeah. And then after capturing states, you have all these setting the random amounts, creating the instruction, then the transaction and all. Now here we have the conservation invariant itself, which says conservation invariant, as it says here. So like I explained, conservation invariance is just checking value preservation across all exchanges, across all deposits, withdrawals, and all instructions. Are we still having same value? Are we still having same token supply? Yeah. So if I uncomment this, I've written an invariant that I said. This just asserts that the amount before is equal to the escrow amount after. So after everything, you should still have the same amount before and after. If not, you should throw an error that conservation violation escrow amount mutated here. So I can save this and decide to run it. Open a new, can just draw this up. Here we run Trident. Okay, we don't have this. Okay, sorry. Trident init. We already had that, sorry. So we run Trident false one. So we can see the assertion. Yeah, some failed. This is the fund flow, which is this fund escrow here. So we can see 1,950 invoked, some failed, 547, and then this. So remember I said first in sent in random input, so some would fail, some would pass, depending on the state of your transaction, instruction rather. Yeah. And now reading through this conservation invariant, you can see conservation violation, escrow amounts mutated here. So and escrow was initialized with this, but you're finding this. This is, if I didn't have this invariant before, let me show you how this works. Let's comment out this asserts. You might have forced, you can see this false. You don't get anything, just probably searching for crashes or just checking this. But when you write in invariants, you catch some bugs, some mistakes from developer. Now, writing this invariant, I was able to see that, oh, for the fund instruction, at some point, in some amounts, the escrows amount gets mutated. You check the fund. So there's an escrow, and let's check the states. It's an amount field, U64. This is simply telling us that at some point, this amount is not what's supposed to be, it's not the initial value. So obviously, it means that there's conservation problem where you start with 100 so and you're ending with 90 so, it doesn't work that way. The token has 1 billion supply, it should have 1 billion supply, regardless of how it's moved around. Yeah, so checking this is simply conservation. And if you check the code, you can spot it. I already marked those parts in the code. Check here, we have fund escrow, so we see it here. Now, the way this escrow works is that when you fund the escrow is initialized first with an amount. Maybe you initialize this escrow with 100 SOL, and the depositor is expected to deposit 100 SOL into that escrow, and then the third party the escrow would validate your deposit and pay it out to, hold on. Let me explain what was here. We have depositor, the counterparty, and all. So supposed to pay out to this person here. But with the way this escrow was written, we can see that instead of validation here, the amount is overwritten. Escrow dot amount is equal to amount instead of like checking if it's equal and then asserting stuff like that. So this is the first error we were able to spot using a first test. So with your regular unit test, you might likely not spot this, or even just randomly fuzzing without invariance, you might not spot this, but with invariance, you get this. Then move to the second invariant. We have talked about state machine errors. Yeah, we move here. Now I did this here. I wrote it in the second, in the exchange part. Yeah. Using variant two, state machine rules via negative testing. Yeah, so let's uncomment this and see what happens. Now, we write this invariance with little to no knowledge of bugs in the system. You understand? You write invariance in like a way of checking security. So prior to this, I'm not aware of the bugs in this system. So I was just writing invariant to just test and then discover bugs like that. That's how it works. Though this escrow is was intentionally designed to be vulnerable, but on a normal day, invariants are just written as a security base. This invariant simply checks if the status of an escrow is not equal to funded. Like let's say I works. We mhm, yeah. So you can see this. So this is an error. See it in code here. So look at the error where the error is coming from. We can see that escrow status was not validated before funding. Before funding, you're supposed to confirm that an escrow is initialized or was initialized before go ahead with funding. But here you can see this part of the code commented out. Hence the error here, where you can see that a new variant was funded regardless of its state. You can see session failed, exchange succeeded, even though the escrow was in status 0. Yeah, so these are the statuses that can end on here. Yeah. So it wasn't funded and we're trying to exchange. This is like how the state machining variant works. Then we have the third one and the last one for now. We have the authorization. Yeah. But I didn't use that. So there's more. There are many ways to write any variants. I just wrote about 3 of them. Now we have state isolation too. We have this. This is under authorization, confirming if the person that cancelled is the original depositor, stuff like that. Where we have a missing signer, somebody sign on behalf of another person. So here we just can uncomment this. So these are new variants. Simply checking if counselor is not equal to depositor, get the escrow status before and after, and then assert to confirm if a random actor successfully altered the state of an escrow. Then you can check that. So this is what this variant does. If I run this first test again, so it depends. If for some transactions you can see this invariant in play. A random actor with this address successfully altered the escrow owned by this person. Now, where's that bug in our program? Check our program. Let's see. Now, this check was commented out. This check that checks if the counselor is the depositor. If I uncheck, if I uncomment this and rebuild this program and try to force, we will not see this error again. Yeah, we can check that out. So that's basically an introduction video to invariants. You might have a longer one on invariants, but this is just showing you what invariants can do. You can simply check the state of your program to understand possible errors, like I said.